Hello, and thanks for clicking on this Prenargulus production. Today, we're going to be talking about exponential functions with the base e. So, e is a special number that we use in math like pi. It shows up all the time in real life scenarios. So, we're going to take a look at how we work with e in some of our exponential function problems. All right, so let's talk about this number e. E is called the natural number because it occurs naturally in the world, in the environment. There are all sorts of scenarios where you're looking at the growth of something and all of a sudden this number E shows up. E is approximately 2.718 and it's a number that continues on forever, such as pi. It's the same idea, okay? You can find the true value of E by calculating 1 plus 1 over x to the x power. This is the equation that describes e, 2.718, for large values of x. So you'd have to put numbers in for x that are extremely large, okay? But the larger the values for x that you plug in, the closer you will get to this true value of e, which is, as we call it here, approximately 2.718. And we're going to be using this approximation to make graphs of exponential functions and then work on some word problems as well. So let's take a look and see what we're planning to do here. So we're going to graph this exponential function with e as its base, okay? G of x is negative 3e to the 2x minus 1. Again, e is about 2.718, 2.71. We're going to use that, okay? But to graph, we're going to use transformations because that's how we know how to make graphs. So let's talk about the parent graph. The parent graph with no transformations would be y equals e to the x, e to the x power. All of these numbers, the negative, the 3, the 2, and the negative 1, all do something to the graph. So the parent is y equals e to the x. Let's talk about the key points on this parent graph. Okay, if I plug in negative 1, I get, let's do it with ordered pairs. We don't need this chart. Okay, so if I plug in negative 1, e to the negative 1 is really 1 over e. So negative 1, comma, 1 over e. If I plug in 0, e to the 0, well, anything to the 0 is 1. And then if I plug in 1, I get e to the 1, which is e. Okay, so we're going to actually graph or write our key points using the variable or the letter e. And then eventually we'll convert them to numbers that we need to actually go ahead and make the graph. All right, so we want to give the true value first, and then we'll approximate it to actually put it on our coordinate plane. So these are our key points, and then this is an exponential function, so there's a horizontal asymptote starting at y equals 0. Okay, let's talk about my transformations here. What do we have? We have 4 things working out. This negative in the front is a reflection over the x-axis, multiplies the y's by negative 1. The 3 is a vertical stretch. Okay, takes the y's, multiplies them by 3. The 2 up here in the exponent is a horizontal shrink. It's going to take the x's and multiply them by 1/2. Remember, anything that's up here with x affects x in the way that you wouldn't expect it to. 2 times x really multiplies the x's by 1/2, the reciprocal of it. Okay, when it says x minus 5, it means you go right 5, right? It means you add 5 to the x's. Okay, and then the minus 1 is in line with the entire equation, so this is going to be down 1. I'm going to take the y's and subtract 1 from them. So, to our key points, we are going to multiply the x's by 1/2, and then for the y's, we're going to multiply them by negative 3. We can do both of these at once, and then subtract 1 from it. All right, so my key points are going to end up at negative 1/2, comma, negative 3 over e minus 1. Well, that's a lot to say. So We're taking negative 3, multiplying it by 1 over e. Let's take a look. Negative 3 times 1 over e. Put a 1 underneath, multiply straight across, and then subtract 1. We're not going to find a common denominator for this because we're going to need it as a decimal in just a minute anyway. 1/2 times 0 is 0. 1 times this is negative 4. And then 1 comma e goes to 1/2 comma negative 3e minus 1. All right. And then my horizontal asymptote, y equals 0. If I multiply 0 by negative 3 and subtract 1, it ends up at y equals negative 1. So here's my horizontal asymptote. There it is. I'll draw it there. We are going to 0, negative 4. That's the easiest point for me to put on here. And then we have negative 1/2, negative 3 over e minus 1. So we're just going to approximate this. You could type it into a calculator, obviously, and get the actual value to go and graph. This is like negative 3 over 2.7 minus 1. So that's almost negative 1 minus 1. So it's just a shade bigger than negative 2. Right? So a shade smaller than negative 2, right? Shade smaller than negative 2. So a shade smaller than negative 2, and then, we're going down. And then over 1/2. So 1/2 comma that. Okay. And then finally we have negative 3e minus 1. So that's negative 3 times 2.7 minus 1. So that's like negative 8.1. It's negative 9. It's not even on this graph down here. So we'll put it down here. And what we have is quickly, this thing heads down to negative infinity. And there's our graph. Okay. All right. So like I said, we're going to give the points with the e's in them, and then we'll just use a calculator or just figure out about where that is on the actual graph on the number line or on the coordinate plane. Okay, let's try the next one. Next one's a little trickier here. If h of x equals e to the negative 4x minus 4, let's talk about the parent graph. The parent graph is y equals e to the x, e to the x. All these things are going to do something to the graph. The key points on that, if I plug in negative 1, I get 1 over e. If I plug in 0, I get 1. And if I plug in 1, I just get e. It's it's an exponential function. So there's a horizontal asymptote on y equals 0. We learned about that in the last video. Now we got to talk about our transformations. But before we do, we actually have to do a little more work here. Because if you look in the exponent here, it's negative 4x minus 4. We can't leave this in this form and state the transformations. We have to take out the GCF. So the GCF is negative 4. We're going to take that out. And if we do, we'd end up with negative 4 times x plus 1. Okay. All right. So let's talk about our transformations. So first things first. Nope. There is a reflection. The negative's up here with x. It's going to take the x's and make them negative. So I'll flip it this way over the y-axis. Takes the x's, multiplies them by negative 1. There is a horizontal shrink. 4 times x really means multiply the x's by a quarter. And we're also going to go left 1. Take the x's and subtract 1. So everything that gets done here, all the transformations reflect x or change x. So we're going to multiply the x coordinates by negative 1/4, both of these at the same time. And then we're going to take 1 away. Y does not change. So negative 1/4 times negative 1 is 1/4. Minus 1 is negative 3/4. 1 over e. Negative 1. 1, and then negative 1 1/4 e. And y equals 0 does not change. So it does not move. So that's y equals 0 still. Okay, we are going to go left 3/4 and up 1 over e. So that's like 1 over 2.7. That's like almost like a third, somewhere between a half and a third. So we'll say there. Left 1, up 1. There we go. And then left 1 1/4 up 2.71, right? So up to there, give or take. So connect these 3 points and it spins down and around here towards the asymptote. And there is our graph. Okay, there's the correct graph. Yes. Again, E is about 2.71, 2.718, somewhere in there. Okay, so again, it's the same old transformations with this fancy number E. E is 2.718. Okay, now we can do the same thing that we did before where we equate the bases, but this one is a little bit more complicated. So if we have a to the x equals a to the y, then x equals y, right? If the two bases are exactly the same on both sides, then the exponents have to be equal. Okay, but notice that this statement says you have one base on one side, one base on the other. This problem doesn't have that. It actually has two bases on the left that are multiplied. They're the same base, but they're multiplied. And on the right, you just have the one base. So I need to simplify what's over here first. So I'm going to do that because I have a property for that. If I have two bases that are multiplied and they're the same, then I can combine them by adding their exponents. And that's what I'm going to do. So I'm going to rewrite this as e to the x squared plus 7x equals e to the 10. Okay, can't add them. They're not like. But now I have two bases that are the same, one on one side and one on the other. So now that means the exponents are equal. X squared plus 7x must equal 10. And now I have to solve this for x. Well, it's quadratic. And how do we solve every quadratic just about in this class? We factor it. Bring the 10 over. We'll have x squared plus 7x minus 10 equals 0. And then we're going to factor it. Find the numbers that multiply to be negative 10 and add up to 7. Negative 10 and add up to 7. That's not going to work because that would have to be negative, negative. So I tell you what, let's change this problem right now. And we're going to make it a negative 10 over here. Negative 10. Okay, working on the fly here. Then we'll add 10 on both sides. And now we get x squared plus 7x plus 10. So now, that'll work. 5 and 2. X plus 5. X plus 2. Split them. X equals negative 5. X equals negative 2. There's my two answers. Sorry about that, folks. Okay. Quick change on the fly there. All right. But we end up with a correct answer here. Both of these numbers, if you plug them in for x, will make this statement or this equation true. All right. Okay, so now we have an application here coming up. Our first application of exponential functions, compound interest. This should interest many of you. See what I did there? Because banks pay out their interest in compound interest. Okay, your savings account, your checking account, CDs, all that sort of stuff. They pay them out using this equation here. A equals P times 1 plus R over N to the NT power. Okay, so when you see, well, let's talk about what all these variables mean, and then we'll talk about what we're doing. So A is the total account balance, or I like to call the after amount. A is the after amount. So after you get the interest in there, how much do you have? P is the principal. That's the money you put in to your account. All right. R is the annual interest rate as a decimal. Okay. You can only do these problems as a decimal for the interest rate. T is the number of years. Okay. And it has to be in years because the interest rate is an annual interest rate. Okay. So T has to be in years. If it's not, so for example, if it says 6 months, well, then you're going to have to use half a year. Okay, you're going to have to use 0.5 for the years. All right. Otherwise, you're going to end up with the wrong answer. Because if you plug t equals 6 in here, it's assuming you're plugging in 6 years. Okay. And n is the number of times per year that the interest is compounded. There's a lot of different ways to do this. You can compound, let's see, you can compound monthly, would be 12, weekly, would be 52. There's 52 weeks in a year. There's 12 months in a year. Daily would be 365 or 366 on a leap year. All right. Semi-annually, or how about quarterly? Quarterly would be 4 times a year. So there's a lot of different ways. It has to tell you how many times a year it's going to compound it. Okay. Literally somewhere in there. All right. Okay. If it says annually, then that's only 1 time a year. Okay. All right. So that's the equation. So again, what we're talking about here is, you have a bank account. Your bank account earns, let's say, 3% interest, annual interest. Your bank accounts compound your interest monthly. Okay. So that would be 12 times a year. So that 3% that you earn is earned over the course of the entire year. So each month you get a portion of that 3% that you'll earn over the whole year. Okay, that's how they all work. That's how you accumulate interest. All right, so let's take a look at a problem here that we can work with. I have $25,000 in a savings account earning 3% interest compounded monthly. That's important. How much money would I have after 10 years? So the way I like to do these is I like to write down my equation. A equals P, 1 plus R over N to the NT power. And then I'm going to write down all the variables, and I'm going to write down what each of those numbers represent. Okay, or what each of them represent. So first thing, I want to know how much I'll have after 10 years. That's the after amount. That's what I don't know. Okay, the principal is the amount of money that I put in. I put in $25,000. R is the interest rate. That's 3%, but I have to write 3% as a decimal. So remember to take a percent, write as a decimal, move your decimal place 2 places to the left, fill in with zeros. That's 0.03. N is the number of times it's compounded. It's compounded monthly, so that's going to be 12 times during the year. And T has to be in years. It is 10 years. Okay, so I'm going to take all these numbers. I'm going to plug them into my equation. I have 25,000. A is what I want to know. 1 plus 0.03 divided by 12 to the N times T power. 12 times 10 power. All right, so now this is going in the calculator. You're going to type this in. It should give you an answer. My suggestion before you type anything into the calculator here is you do the math up top in the exponent. You just don't want to confuse the calculator at all. If you use enough parentheses, you're not going to have a problem. But this one step kind of makes things a little bit easier. So 12 times 10 is 120. So I would literally type this entire expression into the calculator. And if you do, and you're trying on your own, okay, you should come up with $33,733 and about 83 or 84 cents, depending on how you round it. And that is the correct answer. All right. So you should check, make sure you can plug it in and get the right answer. It's important. Okay. And that's how you would do that problem. So if I left my $25,000 in a savings account, never touched it, and it always earned 3% every year for 10 years, when I was done, I'd have 33 grand in that account, which is not too bad. Okay, now, you can also compound continuously. So if you compound continuously, you use that fancy number E, 2.718, as your base. Okay, and the problem becomes a little bit easier. You don't need to give all these information. Okay, A is the amount you have after. Again, P is the principal. R is the growth rate. Okay, again, that would be your interest rate. Again, as a decimal. And T is the number of time periods. Again, in this case, it has to be in years for now. Okay. And it's almost the same equation, right? It's a little simpler. The variables all mean the same thing. All right. Okay, so here you go. You invest $10,000 compounded continuously at an interest rate of 9%. That's unbelievable. You'll never get 9%. How much money will you have after 40 years? So we are going to use what I like to call APERT. because it says it's compounded continuously. That's the only time you can use this equation is when it says it's compounded continuously. Then you can use APERT. So we're going to write down what we're going to find. A, P, R, N, T. A, the amount after, I don't know. Principal is the amount that I put in. I put in 10 grand. The interest rate is 9% or 0.09 as a decimal. Right? Take 9%, move the decimal 2 places to the left, put a decimal, fill in with a 0, and T is 40 years. Okay? All right, so we're going to take these numbers, we're going to plug them in. Whoops, we're not going to plug in P, we're going to plug in a number for that. 10,000 E to the 0.09 times 40. Again, I'll give you the same advice. I would take the 0.09 and multiply by the 40 first. You get 3.6, and then take 10,000 times e to the 3.6 power and type it into the calculator. And if you do that correctly, you will get the following staggering amount: $365,982.34. And that's mostly because of this fancy interest rate, which we'll never get, 9%. That'll never happen. And all the time that we left it in there, 40 years. Okay. And that would be your correct answer. All right. Answers get rounded to 2 places after the decimal. We're talking about money. Okay. And that's it for this. All right. Our adventure into the variable or the number E, 2.718. We can graph, we can solve equations with it, and now we can do some applications with it. Okay. And as always, thanks for clicking.